The universe was supposed to begin in silence, dark, empty, slow. That is the story scientists trusted for decades. A calm beginning, a gradual rise, light taking its time to appear. But something is not right. The James Webb Space Telescope is now looking deeper into space than any instrument before it. And what it is finding is breaking that story apart. Galaxies are showing up far too early, not small, not weak, but massive, bright, fully formed. This should not be happening. According to Greene, this kind of discovery is not just surprising. It could mean something more serious. It could mean that our understanding of the beginning of the universe is incomplete. And if that is true, then the moment when the universe first lit up may not be what scientists believed at all. In this video, you will learn what first light really means in cosmology. You will understand what scientists expected to see after the Big Bang. You will discover what the James Webb Space Telescope is actually seeing, and most importantly, you will see why this discovery is forcing experts to rethink the timeline of the universe itself. Stay with this until the end, because what starts as a simple mystery turns into a deeper question about how everything began. Right after the Big Bang, the universe entered a strange phase. It was filled with energy, then particles, then simple atoms. But there was no light in the way we understand it today. No stars, no galaxies, only a thick fog of hydrogen and helium gas. This period is often called the cosmic dark age. It lasted for millions of years. During this time, gravity was slowly pulling matter together. Tiny clumps of gas began to form. These clumps grew larger and denser. Eventually, the pressure and heat became strong enough to ignite the first stars. That moment changed everything. When the first stars turned on, they flooded the universe with light. This is what scientists call first light. It marks the end of darkness and the beginning of structure in the cosmos. It is one of the most important transitions in the history of the universe. From there, stars grouped together. Galaxies began to form. Over hundreds of millions of years, these structures became larger and more complex. This slow and steady growth is the foundation of modern cosmology. The leading explanation for this process comes from the lambda CDM model. It describes a universe shaped by dark matter and dark energy. According to this model, structure, formation takes time, a lot of time. Early galaxies should be small, faint, irregular. Still in the process of forming, large, well-organized galaxies should only appear much later. That is the expectation. For years, scientists built simulations based on this idea. These simulations matched what telescopes could see. Everything seemed consistent. The timeline made sense. But there was always a limit. Older telescopes could only look so far back in time. The earliest phases of the universe were hidden, too distant, too faint, out of reach. That is why the James Webb Space Telescope was built. This telescope is not just more powerful. It is designed to detect infrared light, which allows it to see objects that are extremely far away. And because light takes time to travel, looking far into space means looking back in time. Webb can see the universe as it was billions of years ago, closer to the beginning than ever before. It is, in a way, a time machine. Scientists expected Webb to confirm existing theories, to show the first galaxies in their early stages, to fill in the missing pieces of a well-understood story, but that is not what happened. Instead, Webb started finding galaxies that looked far too mature, galaxies that should not exist so early in cosmic history. These galaxies are bright, dense, massive. Some appear only a few 100 million years after the Big Bang. That is not enough time. According to current models, there simply has not been enough time for gravity to build structures this large. The process should be slower, much slower, yet the evidence is there. Clear, repeated, hard to ignore. This is where the tension begins. Because if these observations are correct, then something in the model is missing, something fundamental. It could be a small adjustment, or it could be something deeper, a hidden process, a new form of physics, or a misunderstanding of how the early universe behaved. Even more surprising, these findings were not expected to be so strong so early in Webb's mission. Many scientists thought it would take years to uncover anything this unusual. But the data arrived quickly, and it forced a new question. Was the early universe more efficient at building galaxies than we thought? Or are we missing a key piece of the puzzle entirely? This is why voices like Greene are paying close attention. Because moments like this are rare. They signal that science is about to change direction. When observations and theory stop matching, something has to give. Either the data is wrong, or the theory is incomplete. And right now, the data looks very real. That is what makes this discovery so important. It is not just about distant galaxies. It is about the story of how everything began. The first light of the universe was supposed to be simple, predictable, understood. Now, it looks anything but, and this is only the beginning of the mystery. Welcome to the channel. If you want to explore the deepest secrets of space and the universe, make sure you subscribe. Right after the Big Bang, the universe was not filled with stars or galaxies. It was a vast ocean of simple elements, mostly hydrogen, some helium. Nothing more complex existed yet. There was no structure, no light sources, just a thick, expanding cloud of gas spreading in all directions. This early phase followed strict physical rules. As the universe expanded, it cooled, slowly, quietly. Gravity began to take control, but it worked with patience. It pulled tiny regions of gas together over immense stretches of time. These small clumps grew denser, bit by bit. There was no sudden jump, no rapid collapse. Everything moved step by step. Eventually, the pressure inside these gas clouds became strong enough to ignite nuclear fusion. This is how the first stars were born. Scientists call them population 3 stars. These stars were very different from the ones seen today. They contained no heavy elements, only pure hydrogen and helium. Because of this, they burned hotter and brighter, but also lived very short lives. Some may have lasted only a few million years before exploding. Their deaths were violent. When they exploded as supernova, they created the first heavier elements in the universe: carbon, oxygen, iron. These elements would later become the building blocks of planets and life. But even this process took time, a lot of time. According to the lambda-CDM model, the formation of stars and galaxies followed a slow and predictable path. Dark matter played a key role. It acted like a hidden framework, pulling normal matter into place through gravity. Without dark matter, galaxies would not form at all. In this model, small structures appear first. Tiny clusters of stars, weak and scattered. These early galaxies are expected to be faint, irregular, still forming. Over hundreds of millions of years, these small systems merge. They collide. They grow larger. This gradual buildup leads to the massive galaxies seen today. It is a process of accumulation, not speed. Simulations based on this model have been run for decades. Supercomputers recreated the evolution of the universe from its earliest moments. The results always showed the same pattern: slow growth, step by step. Large, bright galaxies should not exist in the early universe. There simply has not been enough time for gravity to shape them. Even under ideal conditions, the process requires hundreds of millions of years, sometimes more than 1 billion. That timeline became a cornerstone of modern cosmology. It shaped how scientists interpreted every observation, every distant galaxy, every faint signal from deep space. The expectation was clear. When looking far enough back in time, the universe should appear young, primitive, unfinished. The first galaxies should look like rough drafts, not final versions. They should be dim, loosely organized, still gathering mass. Anything beyond that would raise questions, because it would suggest that something in this slow, steady process is not behaving as expected. And for a long time, nothing seemed out of place, until the deeper observations began to arrive. Then the data from the James Webb Space Telescope began to arrive. At first, everything looked normal. Faint points of light, distant signals from the early universe. But as the images became clearer, something unusual started to appear. Some of these objects were not faint at all. They were bright, extremely bright, bright enough to suggest large amounts of stars already existed inside them. That was the first warning sign. Brightness in astronomy is not just about light. It tells a deeper story. It reveals how many stars are packed into a galaxy. It shows how much mass is already formed. And these early galaxies looked heavy, far heavier than expected. When scientists measured their distance, the result was even more surprising. These galaxies existed very close to the time of the Big Bang. Some appeared only a few 100 million years after it. That is an extremely short time in cosmic terms. Too short. According to established models, galaxies at that stage should still be in their infancy. Small clusters, weak signals, not fully built systems. But these galaxies told a different story. They looked structured, not chaotic. Their shapes suggested organization. Their light indicated dense regions of stars. Some even showed signs of disk-like forms, which are usually seen in more mature galaxies. This level of development should not exist so early. It was as if the universe skipped steps. Even more surprising was the rate of star formation. The data suggested that stars were forming at incredible speeds inside these galaxies, much faster than models predicted. This kind of rapid formation requires huge amounts of gas collapsing quickly under gravity. But gravity alone should not be enough to move this fast. There is a hidden tension here. To build such massive galaxies in such a short time, something must have accelerated the process. Either the conditions in the early universe were very different, or there are unknown forces at work. Another detail made the situation more intense. Some of these galaxies appeared too compact. Their mass was concentrated into smaller regions than expected. That means they were not just large, they were dense, extremely dense. This raises new questions about how matter behaved in the early universe. Did gas cool faster than expected? Did stars form more efficiently? Or did something else shape these structures in ways not yet understood? As more observations came in, the pattern repeated. It was not a single anomaly. Multiple galaxies showed similar properties. Bright, massive, early. The consistency made it harder to dismiss as error. Astronomers started using a new phrase, impossibly early galaxies. That phrase carries weight. It does not mean impossible in an absolute sense. It means impossible under current understanding, and that distinction matters because science depends on models that match observation. When observation breaks the model, something must change. At first, some researchers questioned the measurements. Distance calculations in astronomy rely on redshift, which can sometimes be tricky. A small error can lead to a big difference in estimated age. But even after adjustments, many of these galaxies remain too early, too bright, too massive. The deeper the data went, the stronger the signal became. This was not a small crack in the theory. It was starting to look like a structural problem. And the more scientists looked, the more these early galaxies refused to behave the way they were supposed to. The problem is not just that these galaxies exist. The problem is how early they exist. For decades, the Lambda CDM model has been the backbone of cosmology. It explains how the universe grows. It describes how matter gathers. It predicts when structures should appear. And until now, it has worked very well. But these new observations are pushing against its limits. According to this model, gravity is the main force that builds galaxies. It pulls matter together over time, slowly, gradually. step by step. There is no shortcut in this process. Dark matter plays a critical role. It forms invisible halos that guide normal matter. Gas falls into these halos. Stars begin to form. Small galaxies grow larger through mergers. This entire chain takes hundreds of millions of years, sometimes even longer, but the galaxies seen by the James Webb Space Telescope seem to ignore that timeline. They are too big, too early. Gravity alone should not be able to build something this massive so quickly. The math does not support it. Even under ideal conditions, there is simply not enough time for matter to collapse and organize at this scale. That creates a serious tension. Because if gravity is not enough, then something else must be involved. This is where dark matter becomes a key question. Scientists assume dark matter behaves in a certain way. It moves slowly. It clumps together. It creates stable structures that grow over time. But these early galaxies suggest a different possibility. Maybe dark matter acted differently in the early universe. Maybe it clumped faster or interacted in ways not yet understood. Some researchers have even suggested that dark matter could have properties that change over time. That idea challenges a core assumption, and it opens the door to new physics. Another possibility is that the process of star formation was far more efficient in the early universe. Gas may have cooled faster, collapsed quicker, turned into stars at a much higher rate. There are hints that early stars were more massive than modern stars. If that is true, they could produce more light in a shorter time. That would make galaxies appear brighter and more developed than expected. But even that may not fully explain the observations. The scale still seems too large. There is also the question of hidden mechanisms, unknown processes that could speed up structure formation. Some theories suggest early bursts of energy. Others point to exotic physics that only existed shortly after the Big Bang. These ideas are still speculative, but they are being taken seriously, because the gap between theory and observation is growing, and that gap is dangerous for any scientific model. When a theory fails to match reality, it faces two outcomes. It can be adjusted, or it can be replaced. Right now, scientists are trying to adjust the model. They are testing new parameters, running new simulations, looking for ways to make the data fit. But the more data that comes in, the harder that becomes. Each new observation adds pressure. Each new galaxy deepens the mystery. And slowly, a deeper question begins to form. Is the problem just a missing detail in the model? Or is the foundation itself incomplete? For scientists like Greene, moments like this are not signs of failure. They are signals. Signals that something important is about to change. In physics, the biggest breakthroughs often begin with small cracks in the system, a result that does not fit, a pattern that refuses to follow the rules. At first, it looks like an error. Then it repeats. Then it spreads. And slowly, it becomes impossible to ignore. Greene often points out that science does not move forward in a straight line. It moves through tension, conflict between what is expected and what is observed. These early galaxies are exactly that kind of tension. They do not destroy the current model, not yet, but they expose its limits. That distinction matters, because the lambda CDM model still explains many things very well. It describes the large-scale structure of the universe. It matches observations of cosmic background radiation. It predicts how galaxies cluster across billions of light years, but no model is perfect. And when new data pushes beyond its boundaries, scientists have to decide how to respond. One path is refinement, adjust the parameters, tweak the assumptions, extend the model without changing its core. The other path is deeper. It involves new physics. Greene has often explored ideas that go beyond standard models, concepts where space and time are not fixed, where the fabric of the universe behaves in ways that are not yet fully understood. These early galaxy observations may be pointing in that direction. If structure formed faster than expected, then something influenced the rules of formation. It could be hidden interactions. It could be new particles. It could be properties of the universe that only existed in its earliest moments. There is also a more profound layer to this, the nature of time itself. In most models, time flows smoothly from the Big Bang onward. Events follow a predictable sequence, because leads to effect. Growth follows a steady path. But if galaxies appear too early, that sequence starts to feel less certain. It raises the possibility that the early universe was not as uniform as assumed, that some regions evolved faster than others, that the conditions for structure formation varied more than expected. Brian Greene often emphasizes that understanding the universe requires questioning even the most basic assumptions. Space, time, matter, energy, all of these may behave differently under extreme conditions. And the early universe was the most extreme. Environment of all. There is a pattern in the history of cosmology. Every major shift began with an anomaly. The motion of planets led to new laws of gravity. Unexpected radiation led to quantum theory. The expansion of the universe led to modern cosmology. Each time, the initial reaction was doubt, then curiosity, then transformation. This situation feels similar. The data from the James Webb Space Telescope is not just adding detail. It is challenging assumptions. And according to Brian Greene, that is where the real progress begins. Not when everything fits, but when something refuses to fit at all. The first response from scientists was caution. Extraordinary claims demand careful checking. And in astronomy, distance is everything. The farther an object is, the further back in time it is being seen. That measurement depends on something called redshift. Light from distant galaxies stretches as the universe expands. The more it stretches, the older and farther the object appears. But redshift is not always simple. Dust, gas, and intense radiation can distort signals. Some wavelengths can mimic others. So one possibility is error. Some of these galaxies might not be as distant as they seem. A small mistake in redshift could move a galaxy forward in time, making it appear older than it really is. Early analyzers relied on photometric redshift, which estimates distance from color patterns. It is fast but less precise. More detailed measurements, called spectroscopic redshift, take longer but provide stronger confirmation. As follow-up observations began, many of these galaxies held their position. The distances stayed extreme. That made the error explanation weaker but not completely gone. Another possibility is overestimation. These galaxies look bright, but brightness does not always mean mass. If the stars inside them are unusual, they could produce more light without having as much material. Early stars may have been very large and very hot. They would shine intensely, making a smaller galaxy appear much bigger. This idea connects to something called a top-heavy stellar population. In this scenario, the early universe produced more massive stars than it does today. These stars burn fast. They emit huge amounts of energy. They could light up a galaxy quickly, but they also die quickly. That creates a strange balance. Bright galaxies could appear early, but maintaining that brightness over time becomes difficult. Some of the observed galaxies seem too stable for this explanation alone. Then there are more radical ideas. Some scientists are exploring changes to gravity itself. The current model assumes gravity behaves the same way across all time. But if gravity was stronger or acted differently in the early universe, matter could collapse faster. This would speed up structure formation. It is a bold idea because gravity is one of the most tested forces in physics. Changing it would affect everything from galaxy, motion to planetary orbits. Another direction focuses on dark matter. Dark matter is invisible, but it shapes the universe. If its properties were slightly different in the past, it could form structures more quickly. Some theories suggest dark matter might interact with itself. Others propose that it could decay or transform over time. Even a small change could have large effects in the early universe. There is also the possibility that the early universe was simply more chaotic than expected. Standard models assume a relatively smooth distribution of matter after the Big Bang. Small fluctuations grow slowly into larger structures. But if those fluctuations were bigger in certain regions, galaxy formation could accelerate locally. This would create pockets of rapid growth, regions where galaxies form much earlier than average. Another lesser-known idea involves cold streams of gas flowing directly into forming galaxies. These streams could feed galaxies with fresh material at high speed, allowing them to build mass quickly without waiting for slow mergers. Simulations have hinted at this process, but its full impact is still unclear. Each explanation tries to solve part of the puzzle, but none of them fully close the gap. And as more data comes in, the pressure builds, because every explanation must match all observations, not just one. Something deeper is starting to take shape. This is no longer just a question about a few strange galaxies. It is about the story of how the universe began to build itself. For a long time, that story felt stable. The timeline was clear. The early universe was simple. Then came stars, then galaxies, then everything else, step by step. But now that sequence looks less certain. The data from the James Webb Space Telescope is forcing scientists to reconsider the earliest chapters of cosmic history. Not in a small way, in a fundamental way. If galaxies can form earlier than expected, then the conditions of the early universe must have been different, more active, more efficient, possibly more extreme. The idea of first light may no longer be a clean transition from darkness to brightness. It may be a chaotic period filled with rapid changes, bursts of star formation, sudden growth, uneven regions evolving at different speeds. That changes the picture completely. Instead of a smooth and predictable beginning, the universe may have gone through a more complex phase, one where multiple processes happened at once. Some of they still unknown. This raises a difficult question. If the early universe behaved differently, how much of the current model needs to change? The lambda CDM model has been extremely successful. It explains large-scale structures. It matches many observations with precision, but success does not guarantee completeness. Science moves forward by testing limits, and right now those limits are being tested. Some scientists believe only small adjustments are needed, slight changes in parameters, improved understanding of star formation, better modeling of gas dynamics. Others see something bigger. They see the possibility that new physics may be required, new rules that apply only under extreme conditions, new interactions that shape the early universe in ways not yet understood. This kind of shift has happened before. The discovery of cosmic expansion changed how the universe was viewed. The detection of background radiation confirmed its origin. Each step forced a revision of old ideas. This moment could be similar. Another detail adds to the tension. If early galaxies form quickly, they may also have influenced their surroundings more strongly. Intense radiation from early stars could have changed nearby regions. Heated gas, altered structure formation, created feedback loops that accelerated growth even further. That means the early universe may not have been passive. It may have been dynamic, self-altering, capable of shaping its own evolution at a faster pace than expected, and this effect could ripple forward through time. The galaxies seen today may carry traces of this early behavior. Hidden patterns, subtle differences in structure, clues that point back to a more complex beginning. This is why the current discoveries matter so much. They are not isolated. They connect to everything, from the first atoms to the largest galaxy clusters, from the earliest light to the present universe. And as more observations come in, the pressure to understand this new picture will only increase. Because the deeper scientists look, the more the universe reveals that its beginning may not follow the simple path once believed. The picture is no longer simple. The universe is not behaving the way it was supposed to. The timeline that once felt solid is starting to bend. Galaxies are appearing too early. Light is arriving sooner than expected. The beginning looks different from the story scientists trusted for years. The James Webb Space Telescope did not just confirm what was known, it exposed something deeper, something that does not fit cleanly into existing models. This is not a failure of science. This is where science becomes stronger. Because every time the universe breaks expectations, it reveals a new layer of truth. The first light of the cosmos was thought to be a quiet transition, darkness turning slowly into structure. But now it looks far more complex, faster, more intense, possibly driven by forces not fully understood. And that changes everything. According to Greene, moments like this mark the edge of discovery. When the data refuses to match the theory, a shift begins, not all at once, but step by step as new ideas replace old assumptions. That shift may already be starting. The deeper scientists look, the more questions appear, not smaller questions, bigger ones, about how galaxies form, about how matter behaves, about the nature of space and time itself. The real mystery is no longer about distant galaxies. It is about the limits of human understanding. Because the more that is discovered, the clearer one thing becomes: there is still so much that remains unknown. If this journey into the early universe caught your attention, stay with this channel. There is much more to uncover. Subscribe and be part of the search for answers that are still hidden in the dark.